Good morning, ladies and gentlemen. It's my great pleasure to give a talk here. And first of all, I would like to thank all the organizers and scientific committee members, including local organizers, for inviting me to a very nice place. And especially, I would like to thank especially Michel and Eric, and also Professor Velasquet and Professor Murad Churi. And this is my second visit to here, Lumini, and I have enjoying, and still I'm enjoying very much, somehow very nice, friendly atmosphere, like, how to say, Arcadian atmosphere maybe. Then take into consideration into that condition, I'd like to speak not very completed, not very firmly structured talk. Therefore, some parts are still incompleted. Therefore, always your discussions and comments are very, very welcome. Okay, then please let me start. This some part, or say 60%, I don't know the percentage, but over 50% based on the joint works with Professor Imanuvilov at Colorado State University. And also, I have one apology, because this talk, I will never touch any numerics. Just I would like to concentrate on mathematical issues. In other words, the uniqueness and the stability for some inverse problems. Okay. Then this is my scheduled contents, like that. Then the main target is compressible fluid dynamics, not incompressible. Compressible fluid dynamics, not usual Navier-Stokes equations. And the two formulations, mostly, maybe this is, not so good. Okay, here, maybe okay, but beginning part is devoted to the inverse problem by Carleman estimate. And finally, I'd like to touch Dirichletto-Neumann approach for stationary Navier-Stokes equations in 2 dimensions. Okay, then, sorry, this is a bit strange, but I think everybody is very familiar with the inverse problem, what the inverse problem is. But however, for making sure, please let me start very, very fundamental or basic part. We are mainly considered inverse source problem. Inverse source problem means that determination of source, say in partial differential equations, by some extra available data. I will not touch so much of the practical significance, but definitely inverse source problem is concerned with the determination of the contaminant source, and also the determination of the mechanism of the earthquakes. Okay. Then already I mentioned that the mathematical subject, the uniqueness and the stability, also some reconstruction, but mainly we would like to consider uniqueness and the stability. And the uniqueness means that for given extra observation data, can we determine unknown, say, source terms uniquely or not? Then the stability issue, that, of course, the continuity of the correspondence from the data to unknown source term. Okay. Then this is very simplified, like a balance sheet. Namely, we have 2 typical formulations of such kind of inverse source problems. The first is Dirichletto-Neumann map or Calderón Problem, which has been very, very celebrated. Other is approached by Carleman estimate. Since Buchgem and Krivanov, the English version appeared in 1981, I remember. Okay, then this is very simplified. If somebody does not like this balance sheet, please be patient. Anyway, then Dirichletto-Neumann map, theoretically, infinitely many measurements are necessary. And the versus Carleman estimate single measurement, or at most the final number of the measurements, or final time of repeat of experiments. Then I think this is better, of course. But on the other hand, initial condition we will consider evolutionary equations, such as parabolic or hyperbolic equation. For Dirichletto-Neumann map approach, no assumptions, say 0 initial conditions are okay. On the other hand, by Carleman estimate approach, one must, this is absolutely necessary condition, namely initial condition must satisfy some positivity condition. This is very bad, quite far away from the practical situation. Then the stability, usually by my understanding, the Dirichletto-Neumann map approach creates logarithmic stability, and on the other hand, Carleman estimate, under some positivity condition, quite frequently, usually one can prove conditional global Lipschitz stability. Then Dirichletto-Neumann map, of course, can work stationary equation such as like elliptic equation, also non-stationary. And I think during this conference, several talks related to that. Then, but the Carleman estimate by nature usually only for non-stationary equation. Okay. Then especially Carleman estimate, I know that various equations, more or less similar methodology can work to produce the uniqueness, and a bit stronger condition on initial value, we can prove the stability. Okay, and now I must keep. Then this is the introduction. This is our main governing equation. Namely, we will consider mainly isothermal compressible fluid. And just for simplicity, I neglect the heat equation. Namely, we will consider always isothermal process. And the first equation is nothing but the conservation law. Law is the density. Then the second is the conservation equation or momentum. The V, this is a vector valued function. V describes the velocity field. This is a three-dimensional vector valued function. And P is the pressure. And usually physically, one can assume constitution equation for P. Therefore, here, I forgot to delete. P is assumed to be a function of density and the temperature, but please neglect the temperature factor. The mu and CV are some constants, and that highlighted in red means the source term causing the flow. Then here is a bit similar situation, a bit different situation, namely capital R is 3 times 3, a matrix function, but given. Then now inverse source problem is the determination of the 3-component function f. F is in R3 valued function by some reasonable data of the density and the V. This is roughly speaking our formulated inverse problem. Okay, then maybe I will skip some basic physical explanation, but of course this comes from some elastic character. And this is a flow effect, advection term. Okay, then in a sense, this equation is a generalization of the Navier-Stokes equation, which is a incompressible fluid dynamics. Okay, but anyway, let us consider taking that equation as a starting point. Okay. Then, as for the fluid dynamics inverse problem, this I would like to mention just very limited references. Sorry, this is not necessarily fluid dynamics. And I have been very glad to write this paper with Imanuvilov because this is by the Carleman estimate approach to prove the Lipschitz stability. But this is more than 10 years ago anyway. Then the point is that, okay, but I will later explain T0 or something. Then as for the Navier-Stokes equation, which we will not consider intensively, but the Navier-Stokes equation, namely incompressible fluid dynamics, I think 2 years ago by Murado Churi and Imanuvilov and Jean-Pierre Pierre and myself proved the global Lipschitz stability for inverse source problem. for Navier-Stokes equations. Also, Gen Nakamura and the Christo and Fan and Zhang considered Bushinesque equation, heat source, inverse heat source problem for Bushinesque equation. Okay. Anyway, this is very rough. Okay. Then what are difficulties? Namely, the method by Carleman estimate for inverse source problem has been already established for single parabolic equation and hyperbolic equation. Therefore, I should mention what the difficulty is. Difficulty is that coupling of the first equation and like a parabolic system. First equation, of course, is the conservation law of the mass. Then parabolic systems like parabolic Lamé, parabolic elasticity equation. Namely, such equation, that one, the principal part are strongly coupled. Then this causes usually difficulty. Okay. Then the stability is described very roughly as follows. Namely, we will prepare two solutions to that the isothermal compressible fluid dynamics. Rho 1 is the density, V1 is the velocity, and F1 is the first possible source terms. Then, and so on. Then our aim is that this is unknown source term, dependent on the X. We would like to estimate L2 norm, for example, by means of some prescribed extra over-determining data, V1, the V and rho. Okay, then this is our main issue. Okay, then already as I mentioned, that key methodology is based on the paper by Buffgem and Kurimanov, 1981, plus some irrelevant Carleman estimate. Then we must treat the first order system plus a parabolic system. Then, of course, first system is like a hyperbolic. Then the parabolic is parabolic. Therefore, those equations are completely different character. Therefore, naturally, proving the combined Carleman estimate, we need some special case. Then there is a related paper by Albano and Tataru. Okay, then this is a bit technical. Yeah, already Carleman estimates are were used at this conference, but the Carleman estimate is roughly speaking some L2 weighted estimate with big parameter. Then this means that for the proving the Carleman estimate, the choice of the weight function is very important. Then roughly two classes. Weight function is very smooth. Weight function has some singularity, like a pole. Then compressible fluid dynamics, singular weight function is impossible because we must treat the hyperbolic type of equation. But the regular weight function is, of course, no problem. This is like a bit technical, but the main techniques, please don't be afraid so much. Anyway, only integration by parts. Maybe also the secondary important thing is that the patience or optimisms, maybe, that's all. These are main ingredients. Okay, then let us start the main Carleman estimate for uncoupled at first. But, okay. Carleman estimate uncoupled parabolic part. Then this is a constant notation. LV is defined by that, namely non-coupling of rho. But the rho appears in compressible fluid dynamics is here. But anyway, we will consider first this kind of, this is maybe not a good terminology, but usually Lamé system is second order in time t, but here we consider parabolic type. Okay, then non-coupled parabolic Lamé equation, however, can admit global Carleman estimate with a singular weight function. Then I would like to show. Then also, maybe this is not so important, but such kind of uncoupled parabolic Lamé system is very useful for solving correspondent inverse problems for Kelvin-Vogt model for viscoelasticity, but I think this is not directly related. Just another background why we will consider such a parabolic Lamé equation. Okay. Okay, then the, sorry, a bit troublesome to state the Carleman estimate, but for the moment, mostly neglect the choice of L function only dependent on t. Okay, some function, but the t equals 0 is 0, then going up and going down at capital T. We will consider time interval from 0 to capital T, then the shape is like that. Then omega, small omega is subdomain of where we take the observation data. Then we will choose some special function, eta, namely outside of omega, non-degenerate. Then we will compose this kind of function. Sorry, this is a bit technical. Therefore, if you are irritated, please neglect that part. But in any case, we can construct rather explicitly the weight function. But the point is that this is a weight function. Then here can be 0. T equals 0 should be 0. T equals 0 and capital T. Therefore, alpha x itself has singularity. Okay. Then. Okay, Carleman estimate is like that for non-coupled parabolic Lamé system. And S is a large parameter. Then this estimate holds uniformly for sufficiently large S. This means that constant C is independent of the choice of S. Then alpha, this is, maybe this will be tired. Okay. Then here is weight function exponential form. S is a large parameter. Then with proportional powers of S and phi, two derivatives, we can estimate of the solution V by means of the right-hand side plus some extra data. Here, small omega is arbitrarily fixed subdomain. But we must assume we must satisfy Dirichlet type boundary condition. Okay, then more or less this shows typical character of the Carleman estimate. Namely, the first of all, Carleman estimate is uniform estimate with large parameter S. Then some weights like that. Then proportional powers to the estimated derivatives. Then proof is not very trivial. We need to do something, but maybe I will skip. But the point is that okay, maybe I will skip. Maybe I will skip. Then the proof is that always for Carleman estimate, or in other words, for unique continuation, strongly coupled system is troublesome because there are several counterexamples by Frisch or somebody else, very famous counterexample for non-uniqueness to the Cauchy problem. Then Carleman estimate always implies the uniqueness of the solution of the Cauchy problem. Therefore, always some degenerate or systems, strongly coupled systems where principal parts are coupled, may make troubles for the proving the Carleman estimate. Then, in principle, no general theory for Carleman estimate for strongly coupled systems. There is one general theory which I know by Calderón, but the Calderón's general theorem for Carleman estimates for the strongly coupled system does not work for like a parabolic Lamé system. Therefore, we need some special technique. But in that case, we have very, very classical technique, namely decoupling. We will introduce divergence as a new function, also curl as a second new function. Then after that, by direct calculations, we can get this kind of diagonalized system, namely weakly coupled system, because this is a second order, just separated, then some lower order coupled. Then we can prove we can apply the usual Carleman estimate for the system, single equation. But But unfortunately, Carleman estimate needs Cauchy data on the boundary, namely Dirichlet and Neumann data. Therefore, in a sense, we can assume Dirichlet and or Cauchy data. But after taking first derivative, we have no boundary data, V1, V2. Then we need to do something. But maybe that part is technical. Okay, then return to use H minus 1 Carleman estimate for single parabolic equation. Then after the first step, decoupling, to apply H minus 1 Carleman estimate with boundary data, like that. Then, but this boundary data, roughly speaking, can be estimated by typical boundary regularity H half and quarter, half in T, quarter in T, half in X. This is, I think, quite classical result. One can find the book by Lyon's Margenes. Then that part can be suitably estimated. Then everything is packed. Then we can get the theorem. Okay, then maybe I will skip like that. Okay. Then the same technique can work for the incompressible Navier-Stokes equation. Then we can prove the similar Carleman estimate. Then by the methodology by Krivanov and Bugge and Krivanov, we can get to the global elliptic stability. Already I referred to that paper. Okay. Then okay. Then but that is non-coupled case. Then what happens coupled case? Therefore, for consideration, we must consider first order, in other words, the transport equation. Because our compressible system is the conservation law equation plus parabolic Lamé equation. Then we will consider very simple first order equation. But we should not be optimistic because this is not so simple. Because our case, hxt comes from the velocity, like a v or something. But then the point is that v may be 0. Therefore, this is like it may, as a priori possibility, this may be degenerate. Or somehow breaking, like a so-called pseudo-convexity, some good condition for proving the Carleman estimate. Of course, for example, if H is a non-zero constant vector, okay, no problem. But H is dependent also X and T, then some component may be 0 or something. Therefore, some special cases are necessary. Then I started to consider. Then I did not find so suitable results. Therefore, I would like to show some my handmade result. Maybe some of you already knows much better result, then your comments are very, very welcome. Okay, then for the moment, we will consider just a single transport equation. Then for simplicity, avoiding for geometric difficulty, we will take a very simple configuration, namely omega is a ball. Then Q is like a cylindrical domain and some regularity H and V. Then I think, I hope the proof is correct, namely assume the vector valued function H has no 0 point up to the boundary. Then some sufficiently large time, U satisfied the transport equation, and U vanishes on the whole boundary. One can conclude that U vanishes everywhere. But the point is that of course, still we must assume. But maybe some sophisticated proof exists, but which I don't know. Then the point is that the stream curve or characteristic is a bit complicated. Therefore, some special case necessary how to propagate the information. Okay. Then this based on the local way. Local Carleman estimate, namely the choice of the weight function on according to non-zero component. Then some like a patchwork, then one can cover the whole domain where U vanishes. But this is rather technical, then maybe I would like to skip. Then, but just I should mention the reference, and related works like inverse problem for the first order equation. I'd like to refer Professor Patricia Gaitan and Dr. Uzan, published, I think, last year, but they considered that case. Then also other paper, but this is like a so-called for Boltzmann equation. Okay, then maybe I will skip that. It's a bit complicated. Okay, then now we'd like to turn to the compressible fluid dynamics, namely coupled by first order conservation law equation plus momentum conservation. Then this is already linearized form or subtracted form, because we will consider a nonlinear inverse problem. The equations are nonlinear in V and rho. Therefore, we should take at first differences, V1 minus V2, rho1 minus rho2. Then already subtracted. Then this is just the notation. The same for avoiding the geometric difficulty, very simple geometry. Of course, we can relax. Then, okay, then small omega, unfortunately, we must take the neighborhood of whole boundary. But this is like an observation boundary. Observation boundary must be the whole. Okay, then, okay, then this is the uniqueness. Okay, in small letters, I have written our governing equation after subtraction. Rho is, of course, the difference between two density functions. Then V also is like a V1 minus V2, the difference between two velocity fields. Then here is like a source term. Then we'd like to conclude F is 0. F is 0 means that inverse source terms can be determined uniquely. Then several conditions, unfortunately, are necessary. Namely, okay, say also T0 must be positive. Then okay, but we must assume like that some determination condition. Then V2 is here. V2 is the vector valued function, but we must assume up to the boundary velocity field of the two. Any one of two never vanish up to the boundary. Then the observation time capital T is sufficiently large. Then if V equals 0 in small omega over the interval and some positive time, two velocity fields are coinciding and rho is also the same, then we can conclude that global uniqueness, namely the difference between two source terms F1 minus F2 is 0 everywhere. This is like the uniqueness for our inverse source problem for isothermal compressible fluid equation. Then this is, in a sense, technical assumption. Of course, if R is identically 0, then we cannot expect any uniqueness, but some strong non-zero condition. And also, this is necessary for applying the Carleman estimate for the transport equation. Then T must be right, but this is very natural because we must treat the hyperbolic equation coming from the conservation law. Therefore, observation time must be sufficiently large. Then also, unfortunately, we must assume that some positive time, T0, we must assume V and rho are 0. Therefore, this is not an inverse problem for the corresponding initial value boundary value problem, because T0 cannot be 0, unfortunately. Then it is very, very difficult open problem whether we can take T0 equals 0. Nobody knows. Then maybe if you are interested, it is worthwhile. You are challenging, but so far nobody succeeded. T0 equals 0. Okay, anyway. Then this is a uniqueness. Then the next is like a stability for the same equation. But maybe you might be exhausted with the Carleman estimate. Therefore, I'd like to skip that part. But roughly speaking, for the same inverse source problem, if we assume a bit more stronger condition, say V2, we can prove the, unfortunately, not Lipschitz, but the Hölder type stability. That's all. Then the fact is a crucial assumption. Namely, V2, say the first or the second or the third, it does not matter, but at least one component of V2 never vanishes. Then for the uniqueness, for the one sufficient condition that the V itself should not be zero. But for the global stability, we must assume stronger condition. There exists some component such that such component never be zero. Okay. Then this is okay. Okay. Then I'd like to touch the corresponding, not exactly corresponding, but some Calderón problem for the Navier-Stokes equations. Then I think this is very, very basic explanation, but yeah, like that. Then this is very classical formulation of the Calderón problem for the conductivity equation. Then, of course, there are many, many practical backgrounds. Okay. Then also, please don't get angry because this is minimum reference. Then as you may know, the Dirichletto-Neumann map of a Calderón problem, the spatial dimensions are very important, namely 2 or greater than or equal to 3, completely different by my understanding. Then the higher dimensions, namely n equals to 3 or greater than 3, then this is very, very celebrated works, and n equal to Adrian Nachmann's paper. But after that, many distinguished works, but I will not mention. Okay, then the next interest is that global uniqueness by partial Cauchy data. Partial Cauchy data mean that this is, I think, has some practical motivation. Namely, original Calderón problem is that we must take all the possible Dirichlet data, compact supports or not, but everything. Then we must observe corresponding Neumann data on the whole boundary. But if we consider very big objective, it's very difficult to observe on all the surface like a globe. Maybe globe is exaggerating, but somehow the partial observation of the Neumann data is very preferable. Therefore, this is so-called partial Cauchy data. Then this is a general formulation, and gamma tilde are subscribed sub-boundaries. Then Dirichlet input like that, some regularity, but they support it in the prescribed gamma. This is like an input sub-boundary. Then gamma tilde, which is like an output sub-boundary. On the gamma tilde, we will observe all the corresponding Neumann data coming the compact supported Dirichlet data. Then can we prove the uniqueness or not? This is a Calderón problem of global uniqueness by partial Cauchy data. Okay. Then also there are several results, and the first is so-called higher dimensions. Victor Isakov, unfortunately, he cannot come here. I think he published as this kind of work, a very early work, 2006. Then after that, this is a very remarkable paper by Koenig and Sjöstrand and Gunther Ullmann, 2007. Then also the Koenig and Saro, I think, last year in already archive proved some general result on the Riemannian manifold. And the two-dimensional case, several results by Ullmann and also with the Imanuvilov. Okay, maybe. Okay, then. Okay, sorry, this is not related with the fluid dynamics, but I cannot resist self-reference. Then last year with Imanuvilov, I have published the three-dimensional case, the uniqueness, with some pairs of a gamma and a gamma chilled. Okay, maybe to somebody, this condition is not very major condition, but technically speaking, this condition is very difficult to relax. Namely, interiors of Dirichlet input sub-boundary and interior of the output normal boundary is empty. But of course, a better situation that this is like the boundary, then input sub-boundary is here, then output sub-boundary is here, then perfectly disjoint and small as possible. This is, of course, the best condition, but so far, nobody knows. Therefore, here is input boundary, sub-boundary, here is output sub-boundary, but only two-dimensional case, the connecting points are only two. Okay, and under some condition, one can prove by partial Cauchy data on gamma, the pair gamma and gamma chilled, we can prove the global uniqueness. Well, then this is, sorry, maybe not so bad to make some self-advertisement, some survey paper in Milano journal last year. Okay. Then, Then now, please let me return to the fluid dynamics and what is the situation, the results of the art of the researches for Navier-Stokes equations. I'm sorry, for the Calderón problem for Navier-Stokes or Stokes equations. Yeah, roughly speaking, 3D case already solved. But the 2D case, when we started, not solved. Therefore, this is the main result in this section. Namely, and 3D case, I think I forgot which is which, but the Lee and Wang, Gennan Wang, and Heck and Gennan Wang and Lee have already solved Navier-Stokes and Stokes system in 3 dimensions. Then my contribution is the corresponding uniqueness result in 2 dimensions, namely in determining the viscosity, mu. Okay, then, sorry. Then, what happens to the stationary Lamé system? Lamé system is also complicated. Then the situation, by the way, is less well known. Okay, 2D case, our method can work. Then 3D case, no global uniqueness. By the global uniqueness, I mean that without any assumption, smallness of unknown coefficients. Of course, if the Lamé coefficients are sufficiently close to constant or something, already proved the uniqueness. But without such a smallness assumption, in the 3-dimensional case, still, by my understanding, an open problem. But the 2D case, removing the smallness condition, we have proved. Then the point is that for the methodology for Navier-Stokes equation and the 2-dimensional Lamé system are same. Therefore, just I refer. Okay, then now quickly I'd like to make a statement of the main result. Then that's all my talk. Then okay, the statement is that at first, sorry, maybe the font is not so convenient to you, but this is like a description of the Navier-Stokes stationary Navier-Stokes equation with variable viscosity mu. If mu is constant, maybe very familiar form appears directly from this. Okay, then here is, of course, we are considered pressure field, 2-dimensional case. Therefore, we have only 2 components. This is a gradient of the pressure field. Okay. Then, at first, okay. I don't know so much the minimum regularity, but unknown viscosity, but say we assume that 10. 10 may be big, but not so big, but I don't know. Then the Dirichletto-Neumann map, this is a usual definition for Navier-Stokes equations. Then F is, sorry, maybe not, okay. F is Dirichlet input. Then we will take Neumann input plus pressure field on the whole boundary. Like that, okay. Then some description of the domain of the Dirichlet map is necessary because for guaranteeing the well-posedness of the corresponding boundary value problem for Navier-Stokes equation. But anyway, this, okay. Then the theorem is as follows. This is maybe a lot of possibilities for the improvement, but so far we assume that boundary trace of unknown mu1 and mu2 must be same, say until 10. Correspond sufficiently many orders. The boundary traces and derivatives must be same. Then the coincidence of the Dirichlet-Neumann map implies the uniqueness in determining the viscosity in whole domain. Okay, then thank you very much. I would like to stop at this point. Thank you very much for your attention. Yes? Okay, for the Carleman estimate approach. I think so, but unfortunately, grounding H-1 Carleman estimate for parabolic equation is proved for boundary data. Then, except for such grounding Carleman estimates, one needs a huge amount of the patience. Then it seems work, but I have never executed. But yes, maybe this might be, or in theory, it must work. but okay. I hope that my answer is satisfactory. Yes.
So here you can determine f of x.
F of x, yes, yes.
Can you allow f of x
Yeah.
depend also on time t?
Unknown f depends on t. Of course, this is a very practical inverse problem. Yeah. But if unknown function f depends on x and t, yeah, then this is like a three-dimensional case for independent variables. Yeah. But the boundary data is only on the boundary. For example, if we take the boundary observation, then this is the lower determining system. Therefore, no expectation. That's why in that case, maybe I think sorry, I don't remember some poster session. For such case, one must, for example, take the Dirichlet-Neumann map approach. Yeah. In that case, not lower determining. But this is a single measurement.
I guess in some cases,
V2. No, because yeah, but the point-wise absolute never vanish. That's enough. The sign plus and or minus yeah does not matter. Oh yes, yes. Otherwise backward. yeah. Sorry. V2. Yeah, something wrong. V2 must be positive. Otherwise, no. Because V2 appears in the conservation law. Therefore, the sign of that part does not matter. Therefore, minus or plus strictly. Yeah, that's enough.
Do you have any other questions? If not, let's thank to the speaker again.
Thank you very much.